Only when we are brave enough to explore the darkness, we will discover the infinite power of our light. Strength doesn't come from physical capacity. It comes from an indomitable will. My dear students, welcome you all in today's class. Today, my discussion will be on conservation of energy. Energy is required for the evolution of life forms on earth. In physics, it is defined as the capacity to do work. We know that energy exists in different forms in our nature. You have learned about various forms of energy like heat energy, electrical energy, nuclear energy, chemical energy, this kind of energies. In this article, we will learn about the laws and principles that govern energy. The law is known as the law of conservation of energy. We will learn that now. Law of conservation of energy. The law of conservation of energy states that energy can neither be created nor be destroyed, although it may be transformed from one form to another form. If you take all forms of energy into account, the total energy of an isolated system always remains constant. All the forms of energy follow the law of conservation of energy. In brief, it states that in a closed system, that is, what is closed system? A system that is isolated from its surroundings. So in a closed system, the total energy of the system is conserved. This is the law of conservation of energy. So, in an isolated system such as the universe, if there is a loss of energy in some part of it, there must be a gain of equal amount of energy in some other part of the universe. Although this principle cannot be proved, but at the same time there is no known example of violation of the law of conservation of energy. If we take UT as the total energy of a system, UI as the initial energy of a system, W work done by or on the system, and Q is the heat added or removed from the system, then the amount of energy in any system is determined by the equation UT, means the total energy of the system, is equal to UI, the initial energy of the system, plus W, that is the work done by the system or on the system, plus Q, that is the heat added or removed from the system. We can write this equation. The change in the internal energy of the system is determined by using one equation, delta U is equal to W plus Q. What is this? Again I am saying the change in internal energy of the system. It is determined by this equation. Now I am coming to a very important part, that is the theoretical verification of conservation of energy. For a freely falling body, the sum of kinetic energy and potential energy is constant. So my motto is to prove that. Okay, so I want to prove that the sum of kinetic energy and potential energy is constant. So to prove this, I have taken one ball of mass m, and the ball is falling from height h towards the ground. Let the mass of the ball be m. Okay, this is position A, position B and position C. From position A, as the body falls down, its potential energy changes into kinetic energy. When it is coming down, gradually it is changing, and at each point of motion, the sum of potential energy and kinetic energy remains unchanged. To verify that one, let us calculate the sum of kinetic energy and potential energy at various positions. That's why I have taken 3 different positions. Clear? Now, A is at a height h above the ground, B is any middle point when the ball is falling, and C is on the ground. In these 3 positions, we will calculate kinetic energy as well as potential energy. At first, we will start from position A, that is from ground it is of height h. So at position A, we will find out kinetic energy and as well as potential energy. Now can you tell me that what is the initial velocity of the body here? The body is falling down from here, that's why the initial velocity is 0, because it is at rest. So at A, initial velocity is 0. So as velocity 0, there must not be any kind of motion, there must not be any kind of energy, so no kinetic energy will be involved here. No kind of kinetic energy will be involved. So that's why kinetic energy equals to 0. Okay, now we have to calculate potential energy. The whole of the energy of the body is potential energy. That's why the potential energy PE equals to mgh. The whole amount of energy is its potential energy. So what is the total amount of energy? Total energy is equal to kinetic energy plus potential energy. Kinetic energy 0, potential energy mgh, it gives us mgh. So at position A, we have seen that the total energy is mgh. Now we will see the amount of kinetic energy and potential energy at B here. What is the amount of kinetic energy and potential energy here? So we will calculate at B. So when the body is falling down from A to B, let it acquires velocity v1, okay, and it finally reaches at B. So whenever it is coming down, let's take that it has covered the distance x. So here the distance acquired by the body is x. So what is the velocity of the body here? Obviously the body was at rest, so initial velocity is 0, and it has travelled the distance x, okay, and the acceleration of the body as it is falling under gravity, so acceleration will be equal to g. So we can write here that the initial velocity is equals to 0 and the distance it travels is equal to x, and the acceleration is actually acceleration due to gravity. So we have considered here these three things. Okay. We know the equation of motion is v square equals to u square plus 2as, where a is the acceleration of the body and s is the distance travelled by the body. Now here v means v1, that is the velocity of the body. So v1 square is equal to, u is 0 here, so 0 plus 2as, a means g and s means x, so we have got 2gx. So v1 square equal to 2gx. Here. Now we know that the kinetic energy equals to half mv square. Here v means v1. So kinetic energy of the body is equal to half m v1 square. Clear? Now in place of v1 square we can put 2gx. So half m into 2gx. So from here this 2 will be cancelled out. We have got mgx. This is the kinetic energy. Okay, now we have to calculate potential energy at B. So at B, at the position B, height of the body above the ground, from ground, what is the height? Full is x, full is h, and from A to B this is x. So the rest part is h minus x. So height of the body from ground is equal to h minus x. We can write this one. Now potential energy, the formula of potential energy is equal to mgh, but h is no longer h here. H means it becomes h minus x. So potential energy mg into h minus x. That gives us mgh minus mgx. What is the total energy here? Total energy means sum of kinetic energy plus potential energy. So kinetic energy here is equal to mgx. So we will put here mgx, and potential energy mgh minus mgx plus mgh minus mgx. So mgx cancelled out. We got mgh. Here also you just look into that. Here also the total energy is mgh. So at position B, at position A, the total energy was mgh. At position B, the total energy mgh. Let us look into the position C. We will see. In the same way, we will calculate the total energy at point C. So at C, what is the total energy here? So at C, let's consider the velocity acquired by the body is v. So when the body reaches here is let it be v. It acquires the velocity v, and the initial velocity u, you know, that was 0. Clear? See, this one is h minus x, but we will calculate now what is the total height, how much distance it is covered. So it is covered the distance, that is h, means s equals to h, and a, that is the acceleration of the body, is actually due to gravity. That's why a equals to g. We know the equation of motion. What is the equation of motion here? V square equals to u square plus 2as. So this is the equation of motion, you know. So from here v becomes v, I told. So v will be v. V square equals to u0. So this one will be 0. 2as. So a and as will be g and h. So it will be 2gh. So we got v square equal to 2gh here. Okay. So kinetic energy we know half mv square, that is half m into 2gh. 2 cancelled out, we got mgh here. So this is the amount of kinetic energy. What is the potential energy here? See, the body is falling under gravity. So at the end, the full energy, the full amount of energy is actually the kinetic energy. So here there is no case of potential energy. Okay, at the ground, when H is 0, what will be the potential energy? mgh means mg into 0, that gives us 0. Okay, so potential energy here is equal to mgh. So at ground H0, it means mg0, that means 0 we have got. What is the total energy? Total energy at point C is given by kinetic energy plus potential energy. So kinetic energy we have got mgh and potential energy 0, that's why it is mgh. See, here also at position C, the energy to total energy is mgh. Okay, I think this full calculation you have understood. So from these equations we can see that the total mechanical energy, means the sum of kinetic energy and potential energy, always remains constant, and each point of motion, and it is equal to the initial potential energy at height h. As the body falls, its potential energy decreases and kinetic energy increases. The potential energy changes into kinetic energy, and just at instant when it strikes the ground, the whole amount of potential energy has changed into kinetic energy. Therefore, the kinetic energy of a body on reaching the ground is equal to the initial potential energy at height h. These two are equal. Okay. Now I am showing you the kinetic energy and potential energy of a body in any kind of vertical motion. So I have taken here downward motion. Okay. And height above the ground. The first column I have taken height above the ground. The second column I have taken kinetic energy, potential energy and the total energy. So at height h, the kinetic energy is 0. Height h means the top height from where the body starts falling. So at that height, the kinetic energy is 0, and I have shown you that the potential energy there is mgh. The whole amount of energy is the potential energy, and total energy becomes mgh. When the body is falling, that time the height becomes h by 2, means I have taken just in the middle. So at height h by 2, kinetic energy becomes mgh, potential energy also. Kinetic energy becomes half mgh, potential energy also half mgh, and that's why the total energy becomes mgh. And at height 0, means on the ground, the kinetic energy is mgh and potential energy becomes 0. So the total energy becomes mgh. So here I am showing you the conservation of mechanical energy in motion under gravity. So this one I am taking as mgh, and this is the maximum height h. So kinetic energy here. So here is the graph of kinetic energy I can show you, and the graph of potential energy I can show you like this. So this one is mgh, and here is the total energy. Okay, and at the middle, that is half mgh. This one is equal to half of mgh. Clear? And this axis showing you the height, and this axis is showing you the energy. It is half mgh. It is mgh. It is 0. So from here, in what conclusion we can come? See, as we take it as potential energy Pe, so at 0, when the energy and the height is 0, see, the height is 0. What is the amount of kinetic energy here? mgh, and potential energy 0. So here potential energy is 0, and see, at the same time the kinetic energy is mgh. This is the graph of kinetic energy Ke. here it is mgh. Okay, so whenever the height increases, means at h by 2 kinetic energy becomes half mgh. So at h by 2 means this height, this is h, so it is h by 2. At height h by 2 the kinetic energy becomes half mgh. Okay, and potential energy also becomes half mgh. Okay, and if we go for height h, that is the maximum height, here kinetic energy is 0. As you can see, the kinetic energy is 0 and potential energy mgh. See here, the potential energy is mgh here at height h. So the total energy is actually mgh. So this is the very important graph, BVI, very important graph. So this graph you practice at home for several times. Okay, I have discussed why this is coming. I think you have understood this part. Here I am showing you a simple pendulum and which follows the conservation of energy. This pendulum is oscillating from a fixed rigid support, that is O, and the A is the resting point of this pendulum. When it is displaced to one side, any one side, and then released, it swings from one end to other end, reaching the equal distance on both of the sides. Okay, and the height, that is h, means from the ground when it is going up, the height it acquires is h. Neglecting the force of friction between bob and the surrounding air, the motion of pendulum can be explained by applying the principle of conservation of energy. How can we explain? See, when the bob of the pendulum is displaced to B, means from A to B, from his position, resting position, the bob gets raised by vertical height h, as I told. So its potential energy increases by mgh. Now on releasing the bob, when we are releasing the bob at B, what will happen? It moves back from B to A. Its vertical height decreases from h to 0 and potential energy is decreasing. How much? Also potential energy was mgh, potential energy becomes 0 and it gets converted into kinetic energy. Clear? That is half mv square. So here at the mean position we can say half mv square is equal to mgh. The full amount of kinetic energy, potential energy, is converted into kinetic energy. At position B, the bob acquires a velocity how much? From here, if we want to calculate V, so V equal to how much? Root under 2gh. From here, from this equation. Okay, so it moves towards C. As it gets the velocity, it will move towards C. At this point C, when the bob raises by a vertical height h above the point A, again it acquires the potential energy mgh and its kinetic energy becomes 0 at position C. As the bob swings back from C to A, the potential energy decreases and kinetic energy increases. And at the position A, that is the mean position, it has its total mechanical energy in the form of kinetic energy and the potential energy becomes 0. So the body swings again from A to B to repeat the process. Thus, during the swing, at the extreme position, that is position B and position C, the bob has only the potential energy, while at the mean position, that is the position A, it has only the kinetic energy. Okay, and in an intermediate state, suppose either here or here, any position, intermediate position, the bob has both the kinetic energy as well as the potential energy, but always the sum of that two energies remains constant throughout the swing. So this one is strictly true only in vacuum where there is no force of friction, as I told you that we will neglect the force of friction of air. So this total conservation of energy of the pendulum bob is only true in vacuum. My dear students, today up to this, you please read it out at home, the full chapter. If any confusion is there, you share with me. Stay home, stay at home, stay safe, and take care of your health. Thank you.